What we have coming up next is a discussion on nuclear thermal propulsion by Mike Houts. He's currently the nuclear research manager at NASA Marshall. He is also, so we have two in the room, he is also a recipient of the NASA Exceptional Technology Achievement Medal. Do you have yours with you? I have mine with me. And is an associate fellow in the AIAA. He will be talking with us about current efforts vis-a-vis nuclear thermal propulsion and about its potential role in enabling ambitious future exploration missions. So, Mike Houts.
Okay, going to actually start out with a video. This is one that NASA's game-changing development program put together for us, and it's actually gives a very good good overview of nuclear thermal propulsion, and then we'll get into some of the details. Also, I will be giving Lee Mason has been doing an excellent job with the Kilopower project. He's up at Glenn Research Center. Unfortunately, he was unable to attend today, and so I'll just be giving a few minutes discussion on Kilopower also, which that project will be very important to enabling the use of fission systems in space.
First-generation nuclear thermal propulsion, or NTP, could enable both faster transit between the Earth and Mars and a series of advanced space missions. Nuclear thermal propulsion is powered by nuclear fission, which has been used on Earth for more than 70 years. How it works is conceptually simple. Energy from fission is used to heat hydrogen to about 4,400 degrees Fahrenheit. This hydrogen is then accelerated through a nozzle, resulting in a propellant efficiency roughly twice that of the best chemical rocket engines. Nuclear thermal propulsion was considered for use in the Apollo program, and significant development and ground testing was accomplished. Advances in technology since the 1960s may improve its affordability, viability, and acceptability. For example, it may be possible to fuel modern NTP systems with low-enriched uranium instead of highly enriched uranium. In addition, it may now be possible to ground test NTP systems at established, safe, self-contained rocket engine test facilities. For human Mars missions, the physical size of an NTP engine is largely determined by the rate at which fission energy can be transferred to the hydrogen propellant. However, the equivalent volume of the uranium that would be split is actually quite small, roughly that of a toy marble. That energy is used to get astronauts to Mars faster. NTP can take months off the trip compared to using traditional chemical systems, reducing risks associated with exposure to galactic cosmic radiation, microgravity, and other hazards of deep space travel. The maturation of nuclear thermal propulsion will also facilitate the development of fission surface power systems, enabling a power-rich environment at any exploration location. Abundant power could also be used for in-situ resource utilization, life support, communication, and other diverse applications. First-generation NTP systems are a first step towards advanced nuclear propulsion systems capable of travel throughout the solar system.
Okay, so for the past several years, really even going back to the time of von Braun, nuclear thermal propulsion, really the big step forward in space exploration that would really benefit from nuclear thermal propulsion, it's always been human Mars missions. It has been considered for, as the video mentioned, use during the Apollo program, used for moon missions, and it does give some benefits, but the big step forward, or the really the leap in exploration that NTP really benefits is Mars exploration. And so several reasons. One is if we just look at round trip time, that was something that Franklin mentioned in his Skype. With an NTP, you can cut the round trip time to Mars from greater than 900 days to less than 500 days. And everything I'm going to be talking about, this is your first generation NTP. I have a few slides at the end talking about where you could go with fission technology in general, or some of the advanced thermal propulsion technologies in particular. But even just the first generation can greatly reduce the round trip travel time, and that of course reduces crew exposure to space radiation, microgravity, other hazards. One way I like to think about it is I don't know if we've really had a major failure in space that we anticipated, because if we had anticipated it, we would have prevented it. In other words, and so just being away from Earth for that long a period of time, having to be totally independent, that in itself is a little bit of a risk that's of course very hard to quantify, but it's still there. The nuclear thermal propulsion, very attractive feature is there's abort modes. With NTP, the efficiency is such that you can effectively bring all the propellant with you on the mission. You don't have to dock with propellant depots in orbit around Mars. And so that saves that step, that critical docking maneuver, some of the critical maneuvers in Mars, around Mars. But also by having all the propellant with you, you end up being able to abort it just about any time. So in other words, it'd be kind of like if you start out with, well, not even sure the best analogy, but once you leave Earth with some architectures, you are committed to going all the way to Mars, because that's where your return propellant is, and you can't turn around. I mean, that's just orbital mechanics. With NTP, you can turn around most of the mission scenarios up to 3 months after Earth departure, some as long as 4 months from Earth departure. When you get to Mars, you can turn around and come back immediately, or you can stay. If we were doing, say, an opposition class mission, you could stay 60 or 80 days, or you could come back in 2 days. Again, just depending on what the situation is at Mars. And so that's a important architectural robustness feature, again, is this ability to return to Earth at any time. The stage and habitat for an NTP system, one of the things we've been looking at recently is moving our external shields, and gives us a lot of benefits, and won't have time to get into the details during this topic. Maybe we can talk some more at the break, but moving the external shields up into the habitat does several things. One, it actually greatly reduces the tank repressurization system that we need during the burn, and so that's a just kind of a more of a propulsion-centric benefit. But it also gives us a lot of water available in the habitat. So that water, it not only helps the ECLIS system. We have probably some of the architectures enough water that you can reduce the recycle requirement of the ECLIS system from, say, 95% down to maybe 70%, or even a little bit lower, which is actually really within the state of the art. But it also, by putting it in the habitat, now the astronauts, you can arrange the workstations so that they receive significantly less cosmic ray dose during the day. They could sleep inside that radiation shelter at night, which really greatly reduces the high energy proton component of their galactic cosmic ray dose. And the habitat would be able to withstand virtually any solar particle event that we could imagine. We have events that we look at, but no one likes to talk about events like the Carrington event, back in, I think it was 1859, just a huge coronal mass ejection. But with with this type of configuration, again, the habitat itself becomes very robust. So that's the benefit of NTP. And I will say a lot of these is we've been looking at how do you turn a bug into a feature. I mean, we need to have radiation shielding with us. Well, depending on where we put that shielding and what we use for shielding, again, it can become a tremendous benefit. And then, of course, it reduces the cadence and total number of SLS launches required. The cadence is particularly important for keeping the cost reasonable. The cislunar space, it does reduce costs, increase flexibility, faster response times, a lot of benefits in cislunar space. And so another benefit of using NTP in cislunar space, of course, be to gain experience using the systems. And also the first generation NTP systems, we see those as a stepping stone for really much more advanced systems. And this is just basically just an orbital mechanics slide, but it shows rather than trying to run up here for our, say, our early human Mars missions, we'll actually be able to run down in here. So you have a much shorter total mission duration, but still have significant time on the Mars surface. And all these topics are really fun, dinner, pizza break type conversations, but we won't have time to go into them a lot, again, during the 25 minutes. Real quickly, do want to mention that fission is fundamentally different than what people would consider a nuclear launch. Nuclear launches to date have always been plutonium-238, at least NASA nuclear launches, and so plutonium-238 is an excellent heat source. You just create the plutonium-238, you radiate Neptunium-237 targets in a reactor, you create the plutonium-238. Once it's created, you will be getting 0.558 watts per gram of plutonium-238, no matter what. And so that's excellent news from a standpoint of you have the heat source there. Was interesting, again, in Franklin's Skype, where he mentioned that sometimes that heat can be an issue. And then that was one of the things that they were running into with the Galileo probe and how they had to, basically deploy it very quickly after the shuttle launch. With fission, it's not quite as simple, but it's close. It's basically put the right materials in the right geometry and it will turn on. And so take any of the standard sized garbage cans around here, you put some water in the garbage can, stir in some slightly enriched uranium, it's going to turn on. You'll get a self-sustaining chain reaction. The reason that happens is it's just a neutron balance. A neutron hits a uranium nucleus. When that nucleus splits, 2 to 3 neutrons are created, and you just need one of those 2 or 3 neutrons to go off and cause another fission. That'll sustain the chain reaction. If we want to increase our power, we just configure the geometry or take advantage of the physics so that slightly more than one of those neutrons will go and cause another fission. Or if we want to decrease power, have slightly less than one of those neutrons. It is very efficient. Also mentioned this morning, fission a kilogram of uranium, that's about as much energy as burning 2,700,000 kilograms of coal. And so a very high energy density, and that's of course what we need in space, compact, high energy density sources. We have flown reactors. The US flew a reactor back in 1965, and of course the former Soviet Union, it flew 33 reactors and had a variety of missions with those reactors. And again, the heat that's generated can be either converted to electricity or used directly to heat a propellant. When propellant's being heated, again, conceptually quite simple. You can think of a hydrogen tank. The hydrogen is pumped through a reactor core, and this is really just a heat exchanger. So it's just a reactor to hydrogen heat exchanger. And because of the low molecular weight of hydrogen, in this particular case, first generation systems will probably be using hydrogen for propellant. At reasonable temperatures, we can get about 900 seconds of specific impulse. And by reasonable, I mean nuclear fuels that can withstand those temperatures for hours. Typically, we can do human Mars missions with less than an hour total burn time. And so again, it's not a very long life system when we're working and operating in nuclear thermal propulsion mode, but it's, again, just conceptually very simple. And so every now and then we'll talk to chemical propulsion people, and they'll say, well, boy, you have one propellant, we've got, say hydrogen and oxygen, we have to worry about combustion instabilities, we have higher pressures, higher temperatures, and so they're wondering what's the big deal? Why haven't we developed nuclear rockets a long time ago? But of course the response is because that is a nuclear reactor there. And so again, it's just a lot of complexities associated with the fact that it is a nuclear heat source. The systems have been worked on extensively in the past from 1955 to 1973 during the Rover Nerva program. There were about 20 NTP engines designed, built, and tested. This was the most powerful reactor ever built. It was designed for 5,000 megawatts. One of the things, again, about fission is it's essentially non-radioactive at launch. In fact, I think we have some discussion in a couple of slides. There's no uniquely hazardous materials on board an NTP system. And so the toxicity of the uranium is actually probably less than the beryllium that we'll be using for our neutron reflector. And beryllium, of course, is launched in satellites all the time. Large quantities of beryllium is launched in certain satellites. And so again, no uniquely hazardous materials, and it's also not an external radiation hazard. The only reason I mention that, most powerful reactor ever built hasn't been run yet, and so you have just 2 guys just riding out with the engine out to the test stand. Now, once the engine has been run, of course, you've generated fission products, and those are radioactive. But before any nuclear reactor has been operated at significant power for a significant period of time, again, it's not an external radiation hazardous, and there are no uniquely hazardous materials on the system. The mentioned in the video about using low-enriched uranium, and this is have to be careful how I phrase this, because for a lot of applications, there's not a tremendous penalty from going to low-enriched uranium. If we look at commercial nuclear power plants, they run maybe 3 to 5% enriched. The definition of low-enriched uranium is anything less than 20% enriched. And by enriched, I just mean the amount of uranium-235 that's in the actual uranium. And so with NTP, we lose some design flexibility by going to low-enriched uranium, but we can still maintain performance. The ISP is really determined by the temperature that the fuel can operate at, and that's independent of the isotopics. And the thrust to weight, we still keep a reasonable thrust to weight with low-enriched uranium. So what we decided to do several years ago would be just to pursue the low-enriched uranium option. Just a lot of it is because of the cost savings and the programmatic savings and flexibility. So it does directly reduce cost related to safeguards and security, but it also gives us a lot of flexibility on the team we can use. There's a lot less restrictions working with low-enriched uranium systems. It's very consistent with programs that have been ongoing for decades. And I'll also mention the policy, U.S. policy. This was a 2012 White House fact sheet. Says the United States is committed to eliminating the use of HEU in all civilian applications, including in the production of medical radioisotopes, because of its direct significance for potential use in nuclear weapons, acts of nuclear terrorism, or other malevolent purposes. So that was just one policy statement. One of the points there, though, is this was actually focused on medical isotopes, and so it's not. That's a very important industry. Very important use of nuclear technology is medical radioisotopes. And so even in that type of industry, there was obviously tremendous pressure to move away from the use of HEU. And so again, for the NTP type systems, that's something that we can't afford to do. That's I guess you'd call those safeguard considerations. It is greatly reduced if LEU is used. In fact, the U.S. encourages. We've been working with other countries to convert their HEU reactors to LEU reactors. So again, it's been again ongoing multi-decade project to go to LEU. So we like the LEU aspects of NTP for those reasons. Now, I did mention the no uniquely hazardous materials and fission systems prior to operations. So if I look at where uranium is used, there's a company right in town here, just a couple miles from here. They actually make spherical shields for industrial radiography sources. So in other words, you have it's pretty heavy, because it's a source that's potent enough to use it for industrial radiography, but you want to shield the operator from it. Well, those shields are made out of depleted uranium. So you have this here. So uranium can actually is an excellent radiation shield, excellent gamma shield. So it's used for that. It's used trim rates in aircraft. The first 500 Boeing 747s had up to 1,500 kilograms of uranium on board, just as trim weights. There's sailboat keels. This was one of the boats that, it's been many years now, but it was one of the, because you think about it's a very high density material, so it's excellent for sailboat keels. And of course, a lot of discussion is used in ammunition, it's used in armor plating. And so, again, I careful to phrase this, but it's not a uniquely hazardous material. It's not just something that NTP has that nobody else would have. Beryllium is used in most modern spacecraft. James Webb Space Telescope has 300 pounds of beryllium on board. And so it's not and we don't have to use beryllium for our neutron reflector, it just gives us better performance. And so try to pick the two, I guess you'd say the material that people will focus on, and again, they're not uniquely hazardous, nothing that's unique to a fission system. Now the primary potential hazard from a fission system is if it inadvertently turns on. Remember we mentioned that it's just, you get the right materials and the right geometry, it will turn on. So need to design the system so that doesn't happen when people are in close proximity. And so worldwide, there have been about 70 criticality accidents since fission was discovered, but there hasn't been one in the United States since the early 1960s. And that's because we've developed the procedures, we've developed the system designs to preclude that from happening. And the affected radius is about 10 feet. So it's, again, but if someone is, say ground ops, other things, you will have people within 10 feet of the system. But that really becomes the, where we want to focus the safety effort. And so again, just very important, these fission systems are completely different than radioisotope systems. And a lot of people also point out it's too bad they're both lumped under nuclear because there's really no similarity between the two. But again, it's so just some of the fission system safety considerations. So with fission, do have tremendous growth potential. An analogy that can be used is this idea of, you had the DC-3, but 29 years later, you had the SR-71. And so we get in this mode where we always want to go right for the SR-71, especially when we talk about, advanced space exploration. That's one of the things that I really liked about the theme of this conference is like, well, how do we, what do we do between now and 2030? And then how do we keep building on that? How do we keep going places with that technology? And so what we're really trying to build with these first generation fission systems is what we would consider the DC-3. And again, by getting used to using the technology, understanding the technology, looking at ways we can do things better, we see just tremendous potential. And again, going eventually to the SR-71. So right now we're looking, solid core, hydrogen propellant, things that people would consider pretty mundane, maybe 900-second specific impulse. But with fission, first of all, there's no reason to stay with a solid core. If we can keep the right materials and the right geometry, you can go liquid core, you can go gas core, you can go plasma core. And it's really with the advances in technology in various fields, those aren't as far out as they might sound, because again, it just needs the right material and the right geometry to keep that chain reaction going, like we discussed in one of the first slides. When you get to, so that's very high performance no matter what. And then one exciting option for really exploring and developing the entire solar system is the fact that advanced NTP systems, you can potentially use any volatile as a propellant. And so I'm going to have some concepts for that. But we talk about hydrogen, but if you go out in the solar system, well, there's lots of sources of water. There's methane, there's ammonia. Kuiper belt objects could be an excellent source. Well, those would all be just fine as a propellant going through a nuclear rocket. And so we would have to configure the system so that you resolve any material compatibility problems. But you think about that, if you had a system that you have essentially unlimited energy density, and anywhere you can get to a source of volatiles, you can use those volatiles as propellant. Well, then there's ways that could potentially be used. And so people talk about everything from just using the Kuiper belt objects where they are to, well, what if you were to essentially dock with a small Kuiper belt object and put some type of a mylar bag or something around that, use the reactor, start heating it up, drive the volatiles off, use those volatiles for propellant, and then nudge that object into a gravity assist off of Neptune. Well, then I'll turn it over to the JPL guys, and then because they seem to be, once they get their first gravity assist, they seem to do just about anything. And so, but then you could conceivably put that object with its huge source of volatiles and resources anywhere in the solar system that we wanted it. And that would be, again, just using, but it would need a energy source such as fission, just because you're not burning the volatiles, but it would just use those volatiles as propellant, but just to nudge it enough to get to that particular gravity assist. And so people even talk about maybe being able to terraform with that. If we could add enough volatiles to, say, Mars, then again, could you add enough, is there enough volatiles in the Kuiper belt or elsewhere in the solar system to actually be able to really, truly terraform a planet? And by the way, I love being able to talk about this stuff. Most conferences I go to, I don't get anywhere near into stuff like this. So this is fantastic. But again, if we're really looking at, okay, we want people to be able to utilize the solar system, these are the kinds of things that might be beneficial. Now, the different types of rockets, this would, you have the solid core that we're talking about today. One of the things on the liquid core, and I think Roger Lennard's going to be talking later today, Jonathan Witter also, there was a concept that James Powell had come up with, is the particle bed reactor. But one idea that people have mentioned is, well, what if I took that particle bed, and basically you'll see the schematics of it, but the core is about this big around. It has little particle beds with radial inflow, depending on the concept, maybe like 37 of those smaller cylinders inside this larger cylinder. I believe some of his concept he used a lithium hydride moderator, but anyway, in the concept. Well, what if I took that and I replaced it with a centrifuge made out of neutronically friendly materials, which they exist. Well, now what I could do, you picture this, instead of being the full core, just small cores, I can bleed any propellant in along here I want to. So that could be water, ammonia, methane, hydrogen. That propellant then goes through the wall of the centrifuge. And again, this is all I think John mentioned, physics versus engineering. So this hurts to say as an engineer, but it's a lot of fun to say, just my inner physics person. But anyway, but if I can figure out how to bleed that propellant and keep that wall cool, well, now that wall, it's going to be compatible with just about anything. I mean, there's all kinds of materials that are compatible, room temperature, maybe 400 or 500 Kelvin with ammonia and water and methane, any of the volatiles I might have. That propellant bleeds in. Now this be the uranium-bearing region, and it can be solid along the edge because it's still cool. The propellant's cooling it, but it can be liquid in the middle. And because I'm spinning, because it's in a centrifuge, that uranium, which is very heavy, is going to be held to the outside, and whatever volatile I have, which will probably have been dissociated at that point, go to the middle and out the nozzle. And so that was the liquid core idea. And all these concepts were popular in the late 60s, early 70s in different forms, but with this particular concept, they were estimating maybe 1,800, 2,000 second ISP with hydrogen, which is exciting. I mean, that's very good for a high thrust system, but it's also exciting because I can use any volatile I want to as a propellant, that type of system. Then you have open cycle gas core nuclear rockets, closed cycle gas core rockets. Here's where you basically you go ahead and let the uranium become a plasma, and then you use basically either your fluid flow or maybe some concepts use magnetic fields to try to hold on to that plasma, and you heat the hydrogen radiatively primarily from that plasma. There's actually a fair amount of thought that went into these types of systems, but a lot of challenges, as you can imagine. But there you're looking at 3,000 to 5,000 second specific impulse, again at a very high thrust. And so there's some papers, if you go back to the old Journal of Spacecraft and Rockets, they would talk about getting to Mars in 30 days and all these other ideas, these types of systems. And so those are just some of the ones that are out there. Now, the other, I guess you would say, application then is once we have these types of advanced fission systems, you don't have to only do thermal propulsion with them. You can also do electric, generate power that gives us the power-rich environment anywhere we'd like, and also use those power systems, if they're very high performance, to propel, say to drive a Vasimir or some other type of electric propulsion system. And so this is a chart. This is actually put together by Lee Mason. He made the slides for the next talk I'll be given briefly. But again, just showing when you get up into the, say you went into a direct gas Brayton, this would be, say you had a Brayton cycle where you had turbine inlet temperatures, maybe 1,800 or even a little bit higher Kelvin potential. That's where you get down into this range where you're just a few kilograms per kilowatt electric. And so that's where you can also have very exciting performance from electric propulsion system. But also if we start doing extensive ISRU, if we start using the, say some of the magnetic launchers off of the surface of the moon or the surface of Mars where you need very high power levels. This would, again, make systems that would be affordable from a mass standpoint. With a nuclear rocket core, generating gas in this temperature range, I mean, we're actually generating gas that's probably 1,000 degrees Kelvin hotter. Now, granted, the nuclear rocket only does it for a couple hours, but again, the idea being work with fuels that could potentially be dialed down a little bit in temperature and have a much longer lifetime. And so with that NTP derived system, again, hopefully enable some of these very high performance systems that are talked about here. Again, just observation, space fission power propulsion systems, game-changing technologies for space exploration. We see these first generation systems, very, very significant benefits. Earth-Mars transit times of 120 days, talking about 540-day total Mars mission times. Again, just a lot of the benefits for some of the very early systems. And again, very robust, very safe, can abort at most times of mission. No one wants to talk about having to abort their mission, but it's nice to have that safety feature in the system. And so again, that's just the first generation system. And then of course the advanced systems can lead to some, again, some very, very exciting scenarios. So let's go ahead and maybe switch over to Lee Mason's charts from the back here. What the Kilopower project is focused on is really trying to find the first, I guess I would say, useful fission power system. And so looking at what we can do with the radioisotopes, it's very, very hard to get a radioisotope system over a few hundred watts. It's just from everything from the launch to the availability of the plutonium-238. And so once you get to about a kilowatt, that's where fission might start to play. And then, and I'd say maybe the 1 to 10 kilowatt electric range, and that's where kilopower is focused. You can have some extremely simple fission devices. And so the idea is you take a small core, and it's a solid core. It's a U7 uranium metal with 7.5% molybdenum mix in it. And actually, Chris Robinson, who's somewhere in the audience back there, Y12 actually made this core for the kilopower, and they did a fantastic job. They made it in 3 sections, and then it's this metal fuel, has very high uranium density. So, I mean, really tiny. I'm probably making it too big already. And the heat that's generated by fission in that core conducts to the edge of the reactor into heat pipes, and then that heat is transferred to a power conversion system, be it Stirling or thermoelectric or another type of power conversion. And so there's no flowing coolant. Heat pipes are passive. The system at some power levels, it can be set up so even once it's running, you don't even need to turn the control drum. That goes back to the energy density of uranium. Yeah, it's generating some very useful electricity, but it's burning uranium at such a low rate that it actually can just run off of what they call the temperature coefficient, just to keep the system running. So again, can make a very simple system. And so what they did, and this was, I think I talked about a lot of this, it was again using sodium heat pipes. And again, I'll refer you to Lee Mason up at Glenn if you have more details, or Chris Robinson in back want more details on the system. But what they did then is they went ahead and they actually built and ran this, and this is what was so significant. And so they went out to, again, Y12 made the core for them. They had beryllium reflectors made, and they went out to the device assembly facility out in Nevada, and they actually ran the system at full power. And so they did, I think it was on the order of 28 hours of full power runtime, and just showed that it worked exactly as expected. And so and so that was a very, there has been a lot of press on kilopower. The experiment itself was called the Krusty experiment. If you haven't been looking for it, you might not have noticed it. But if you go back and you just search under kilopower or Krusty, you'll pull up a lot of very good articles describing the system. But again, it had flight-like components, very realistic configuration interfaces. They did flight-like conditions. It wasn't a vacuum environment. And then they and all of the, just the models, the ground safety issues, nuclear test operations, transport assembly, all of those issues were very realistic. So gained a lot of information, especially the models. I remember one of the individuals modeling, Dave Poston at Los Alamos National Laboratory, and he's really, really good at, well, lots of things, but modeling space reactors. I remember once there was one test, I think they were running, and he thought that he had what you call temperature coefficient. The core starts to expand, and as the core expands, as it's getting hotter, it'll actually turn the system off, which is good. I mean, it's a passive safety. If you think of the system heats up, the core expands, same mass of fuel, but a larger surface area, you have more neutrons escaping, so it shuts the system down. So a nice passive safety feature. And I probably have the numbers wrong, but I just remember it was something on the order of, he thought it was going to turn over at 460 C, and it turned over at like 459.4 C, and he was just distraught. I mean, how could he miss that? So anyway, they had some really good modeling efforts, some really good, good models, and really sharp people working on this particular project. Here's some of the actual hardware being put together. A lot of the work, they couldn't ship the highly enriched uranium up to Glenn Research Center, but they could certainly do a lot of mock-ups. I believe Y12 also had made some depleted uranium sections for them to use, so that they could put everything together, try the mock-ups again at a lot of this, the system levels done at Glenn Research Center. I think that's Mark Gibson. Have trouble. Everybody wears the same clothes. Have trouble recognizing them, but up at Glenn Research Center, and again, just showing some of the work that they completed. But again, everything went as planned, as predicted, and a really good job exercising the team. The potential applications that have been identified for kilopower. Think of what the goal here really is to get a fission system launched, get it used in space. And so, but no one's, I mean, and you always have this debate, well, why don't we just launch one just to show we can? And it's a modern fission system. Again, there were a lot launched. I think the Russians were launching even through the late 80s. But just a modern, 2018 going into 2019 fission system, launch it so we can operate it, learn how to use it. But there never seems to be just enough momentum to just do a true demo flight. So there always has to be something useful that's done by the mission. And then, of course, we get into that mode where people get too excited, and now all of a sudden you have a $1 billion payload, and nobody wants to put your experimental power source on their $1 billion payload. So so there's this balance there that we always struggle with. But some of the missions that have been talked about, human Mars surface missions. But what if we did lunar surface operations and we just put a kilopower down in one of those permanently shaded regions, maybe generating a kilowatt, maybe a few kilowatts electric, and use it to recharge rovers. So now all of a sudden I can have rovers coming back, charging up their batteries off the kilopower, go out as far as they can rove. I could possibly configure radiators if I could use the thermal heat in a certain way that I wanted to. So you start thinking, if you get into the details, it could actually be some pretty simple, in this case it would just be a kilopower with some rovers that were able to find it and recharge off of it. But some pretty simple missions that would still get us into this mode of actually being able to use fission systems. So that's one that's being talked about a fair amount now. Of course, planetary orbiters and landers. If you get out into the outer planets, sometimes we've learned to get by with very, very little power. But even for a science mission, if you had to, say 2 or 3 kilowatts instead of 200 or 300 watts, that can make things easier. You don't need to go to really high power because we're not used to using really high power levels. But even just getting the data back from New Horizons, everything worked perfectly and we got it back over the period of a year. But it wouldn't have been horrible to get it back over the period of a month. So it's and so again, a lot of potential uses for the higher power system, and then. Down the road, commercial missions, terrestrial adaptations, power uses. These are probably more the what we'd call like an NTP derived system. And so I know just one theme to take away would be, start out with fission. We need to get reactors running in space. We need to start out with something really simple. There's always going to be missions that we can do with kilopower class systems where this 1 to 10 kilowatt range, and there's always going to be used for a few horsepower internal combustion engines. And so it's not so those are always going to be useful, but then also use that experience to help us develop the higher power type systems. And again, we would say NTP derived system, either use the nuclear thermal propulsion directly, like talked about in the first talk, or go ahead and take a close derivative of that NTP reactor, a close derivative of that system, of the fuel, the core configuration, the control systems. Take a very close derivative of that, but maybe use it to generate a lot of electricity. And so again, either powering an ISRU or either an ISRU or possibly an electric propulsion system. So with that, I think I'm right at my 37-minute allotment, and so we will go ahead and go on to the next speaker. Thanks.